Summer is just around the corner, and we may be facing one of the hottest seasons in decades. That's why, together with the Mr. I Poo channel, we decided to collaborate and build a homemade desktop air conditioner that can also be used as a cooler for Coca-Cola or any other drink. On my channel, you'll see detailed instructions and discover important details that may not have been fully explained in my previous videos on this topic. We'll break down all the myths and use a timer to prove that this is real freezing happening in real time. So sit back, make yourself a cup of tea, grab a sweet bun, and let's get started. Like any air conditioner, refrigerator, or ice maker, this device operates using the principle of a vapor compression refrigeration system. The main components of such a system are a compressor, a refrigerant, and copper tubes of different diameters forming a closed loop. Copper tubes of 3 different diameters are used as heat exchange elements. The largest diameter tube will be used to create the condenser, the medium diameter tube will serve as the evaporator, and the thinnest tube will function as the capillary tube, acting as the expansion and metering device. During operation, the refrigerant circulates through the closed system, continuously changing from liquid to gaseous state and back again. Due to pressure and temperature changes in different sections of the system, heat transfer occurs. Inside the evaporator, the refrigerant absorbs heat intensively, creating the cooling effect, while inside the condenser, it releases the accumulated heat into the surrounding environment. The capillary tube length for our small cooling system should be approximately 15 centimeters. It can be left straight or coiled into a spiral shape. The form itself has little effect on the system's performance. The most important thing is to make sure the tube has no sharp bends or kinks that could restrict or completely block the refrigerant flow. To create a more compact design, we wrapped the capillary tube around a perfume cap, resulting in a neat and convenient shape. In addition to the high-pressure compressor capable of compressing the refrigerant to the required operating state, an electronic control board will also be needed to manage the electrical part of the system. Since the board was specifically designed for our application, it will serve 2 purposes at once: controlling the electrical components of the device, while also acting as the main structural platform on which the entire cooling system will be mounted. For manufacturing the PCB, I once again used JLC PCB. I've already ordered many different 1 to 4 layer boards from them for previous DIY and engineering projects, and the quality and delivery speed have always been excellent. What's especially interesting now is that JLC PCB is actively expanding into higher performance multi-layer PCB manufacturing, especially 6-layer boards. These boards make routing much easier in complex projects, increase wiring density, and allow engineers to build more compact and efficient devices. They also offer free VIA in-pad support and ENIG surface finish for 6-layer PCBs. features that are usually only available through much more expensive manufacturing services. In addition, JLC PCB supports plus or minus 10% impedance control, which is especially useful for high-speed designs, IoT devices, FPGA projects, advanced MCUs, and wireless modules. And despite all of that, the pricing remains very affordable. Professional-grade 6-layer PCBs are usually expensive, but JLC PCB makes them accessible even for makers and independent engineers. Right now, small-size 6-layer PCBs, starting at 50 by 50 millimeters, cost only around $2, and new users can also get a $30 coupon for their first order. Every board also goes through 100% flying probe testing and 4-wire Kelvin testing to ensure electrical reliability. If you're interested in trying multi-layer PCBs for your own projects, you'll find the links and coupons in the description and pinned comment below. If you're interested in trying multi-layer PCBs for your own projects, you'll find the links and coupons in the description and pinned comment below. The air conditioner housing consists of two parts, electronic printed circuit boards. We will connect them together using these bolts and nuts, which are perfectly suited for our project. We tried making evaporators with different designs. The first two versions turned out to be unsuccessful because they did not distribute the heat very well, which the fan was supposed to cool down. Due to poor heat exchange, we decided to create the evaporator in the same spiral shape as the condenser, since this design proved to be much more efficient and compact. Thanks to 3 batteries that can be removed and reinstalled with a single click, our air conditioner will operate. That's why we are adding a small chamfer which works as a guide, making it easier for the battery contacts to align and connect with the contacts on the electronic circuit boards. When soldering copper tubes, It is essential to use flux and proper soldering equipment that provides stable heating. It is also recommended to use high-quality solder with a high melting point. Otherwise, when the condenser heats up, the joint may weaken and lose its seal. An air conditioner is a system that controls temperature, humidity, and air movement in a space, creating comfortable conditions for people or equipment. At the core of most air conditioners is a refrigeration cycle that uses a refrigerant. It continuously changes from liquid to gas and back again, transferring heat from one place to another. In simple terms, an air conditioner does not create cold. It removes heat from the room and releases it outside. Main components of the system: compressor and the heart of the air conditioner. It compresses the refrigerant, increasing its pressure and temperature. Condenser, a radiator where the hot gas releases heat to the outside air and turns back into a liquid. Evaporator, located inside the room. Here, the refrigerant evaporates again and absorbs heat from the air, cooling it down. Expansion device, capillary tube, or expansion valve reduces the refrigerant pressure before it enters the evaporator. An interesting point: the efficiency of an air conditioner strongly depends on heat exchange. That's why, in DIY systems, it is so important to properly design the shape of the evaporator and condenser, airflow from fans, and surface area. Even small mistakes in heat transfer can significantly reduce performance. In simple terms, an air conditioner is a heat transporter that continuously moves energy from inside to outside, creating a cooling effect indoors. I decided to run another test to see how our air conditioner performs under real working conditions. Honestly, I expected a normal cooling effect, but the result turned out to be even more interesting than I thought. Right after the system started, a noticeable temperature drop began. The airflow quickly became colder, and within a short time the first effect appeared. The surface of the tube started to sweat, and then a light layer of frost gradually formed. And the most surprising part is that the cooling is not just stable, it develops very quickly. At some point you can clearly see ice forming on the tubes, which indicates strong heat exchange inside the system. To keep everything clear and honest, I placed a simple clock next to it. This is just a basic time reference, so everyone can see that there is no speed up, no editing tricks, or any effects. Everything is happening in real time. I intentionally kept it as one continuous shot, without cuts or effects, so you can observe the entire process from the start all the way to the moment when the system reaches full operating performance. And this is exactly the most interesting part, when a simple DIY build starts behaving almost like a real refrigeration system with visible icing and stable cooling performance.